All right. So at this point, we are waiting once again. uh, Nothing good comes easy. It takes effort. So let's build our model. We can even do that here. So the y we don't know. We say BO. BO is your intercept, which is minus 530.7237 324 plus, you open brackets, B1, which is the molar weight, 3.091. I don't think if I'll be writing all the figures. 3.091, maybe stop at the just 3.091 is okay. Times,
It's significant to us.
yeah,
Okay.
3.091 times, yeah, because now it's times, right? Times the first variable here. Oh, this thing have not blocked my variable. Okay, the first variable is C23 times C23 for my own. So I can see C23, good, close bracket, then plus, open bracket, the coefficient for hydrogen bond acceptor minus 55.4122, then times D23, close bracket for my own, plus, open bracket, the coefficient of hydrogen bond don't know, 129.1469 times E23, close bracket, plus, open bracket, TPSA 8.45519 times F23 for mine, close bracket, plus, open bracket, minus 159.628709 times G23, close bracket, then plus my residue, which is the E, the epsilon, 349.2649885. So this is easier. Then enter.
What did you get? What did you get? One one
1131.
three one
Yeah,
point. I got 90. All right.
no problem. So
Continue.
I can drag down, just drag it down now.
Madam, are you? Oh,
Hello, sir.
okay, I'm finished. I can see the screen now.
All right. So,
Yes,
Don't mind
so
me. Oh.
no, no, no,
We
no.
have been involved in conference. So I did I have made presentation today.
Chai, congratulations. So, we have been able to predict their biological
Thank you.
activity and this is telling you, this is just to now we can now see the predicted blood flow activity of our our own test data of our test data, but this is just for training. So we can now, if we want to now do docking, now let me now tell you the application, the relevance of this, because now, based on my experience, some persons can do this and publish. Oh, yeah, because you have just predicted the biological activity of your new compounds. But then, if you want to do this as project, here we have just 19 training data. We are supposed to have up to at least 100 training data, so that the model can be well trained. So the model can be well trained with multiple variable data. So, but here we are just using uh, just 19 for learning purpose. Yeah, and then we are supposed to have a large number of test data. Now, usually our training data covers 70% of our total data, while the test data covers 30% of our total data. So if you have to work with a total of 100 data, we'll just share it. 70 will
Means
be our training
that
data,
training.
which is the known one, the one that has the known activity, while 30 will not be from the ones that has the unknown activity which we are predicting. Now, let me now tell you actually the relevance and the application of this. If okay, I'm coming.
Oh,
Now, uh, the application of this is we are going to, I think we have not done something which is
Are you sharing your screen?
yeah, my screen is on.
Okay. Let me tell me. Let me up and come back again.
Okay, so we have not done one thing which is optimization, like structural optimization. I don't mean the one we did in the energy minimization. Here we can now decide to build, we can now decide to, since we are working on entrepreneur, we can say to, okay, let me modify different, and let me use one entrepreneur and modify the structure, so I can have 100 modified entrepreneur. We call them analogs or derivatives. So I can use like what we use today. The 5 test data we use today are all entrepreneurs, but if you look at them, the difference is there are just a spatial difference in the structure. Here OH might be at number 1, the other one OH will be at number 4. The other one OH might be at number 1 and 2. So just different differences. So we can do that by ourselves now. We can choose Indo derivatives, build 100 Indo derivatives by putting or substituting the positions of the groups or the functional groups. So we can do that because we have already done a term draw. So we can do that even without we going back to term draw. We'll just create a table of substitution showing the substitution and then build 100. Now you end up seeing that those ones you have modeled by yourself are novel. They may not be found in PubK. So what you now do is to use the term draw to generate their SMILE code and then come to Swiss admin. Because why they may not be found in PubChem, PubChem is a depository database. It does not work with algorithm. It works with what is already stored in it. But Swiss admin is it works with function, with algorithm. So if you can model these 100 derivatives, you can now use, after you have modeled them, you optimize them, you save, you use your term draw, get their SMILE code, then come to Swiss admin, get their properties, then build this model. You can choose to have 200 data, 200 training sets, but make sure you have large training sets, no less than 100. The last one we did, in fact, we had total of the work I did, I had total of 7,000 data in total. So now, by the time you have modeled 100 derivatives of indole, then you use this model to predict the activity. Now just you can imagine this 4, just this 5. From here, if I want to further this dotting, I can now interpret this result that out of these five derivatives that we work on, I really don't know the name of this one, but it's having 724, which is a bit lower than others. So it means that out of these 5 derivatives we use, whoever is this 724,
Is that Modine?
Modine, right? All right. That it is more potent than others against malaria. So that is the relevance. So I just know that Modine can target malaria receptor than these 5 because of the model I built. Without me even conducting any laboratory experiment on the Modine, because we know that the activity of a structure is as a result of the properties of that structure. So you can also decide to increase the properties. You can add other properties. Like, let me come to Swiss admin. Okay, in this Swiss admin, you see these properties here. 1, 2, 3, 4, 5, 6. These 6 properties are also relevant in draw design, so you can include 6 of them. Although we have already included size, we have included polarity, which is a TPSA. We can include insolubility and lipophilicity, flexibility and insaturation. So we can bring in more and have like 10 variables so that the model can be well trained. So when you now have 100 model structure that we have tested, from there you can pick like 10, the ones that have the lowest biological activity. You can pick like 10. Only that is a paper. You have published it. Yeah, you have done a paper. You just have a paper. Maybe in that paper now, you can design the topic to be de novo modeling and QSA analysis of pyridine derivatives against malaria targets. So I just formed the topic now, and I can do that. De novo modeling means that you model those compounds with your system. So one can work on that area. I have seen some papers on these areas whereby we can now predict the biological activity without conducting lab experiment. But then what I do is, out of these 100 modeled derivatives I did and tested them using ligand based, I can pick 10 that has the lowest activity, the best activity. From that 10 now, I will take that 10 to docking. I will now use that 10 for structure based drug design, because ligand based has helped me to identify active compounds, 10 active compounds out of my whole test data. I will now use those ones for docking. That means I am expecting to have better results, because I have identified the potent compounds. So I will now go for docking just to validate my results. So that is the essence of all these process we have been running around in ligand-based structural design. So at this point, I would like to take some questions and the interactions. So before I proceed to QSPR, if we have time, but I'll proceed to QSPR. We just finished QSAR now. So any question? Yeah, if you have, you can indicate.
Yeah, go back to that formula for multiple linear regression and then explain more on how to apply it. That is how to give computer command to execute it. I
Okay.
think I was lost when you were saying something.
Okay. So can you see my screen?
Yes, I can see it.
Okay. So the formula on the screen is the multiple linear regression. Y is the output, and the S is the input variable. So what the formula just need you is to get the B. These B's are your coefficients. So the B are the coefficients. The BO here is intercept. While the B1 is the coefficient of the first variable, S1. Then the B2 is the coefficient of the second variable. The B3 is the coefficient of the third variable, and so on, depending on your number of variables, up to Bn, Sn. Then the E is the standard error of the whole data. The standard error of the whole data. So what we'll do is to create a table of our data and their S. This S now is their variables. So when we do that, we'll now use regression
Your voice
equation.
is
Yeah. So when we do that, like see what we did now, we okay. So we had
your voice is breaking.
okay. We had
Hey,
those variables. These are the S variables. These
I
variables
was even
are
thinking it was me.
the S variables. So what we now do now is to use them to build the equation. So we built the model and we got these constants. We got these constants. So these constants we are gotten from the model. So the intercept here, this intercept is your BO. So this intercept is now the BO. These are coefficients. All these coefficients are the B's. This this one for intercept is the BO. This one is the intercept of molar weight, the intercept of hydrogen bond acceptor, the intercept of hydrogen bond donor, the intercept of TPSA. So you will now type in that equation. So we came here. This was what we typed in. For the first one, the equation stated. Okay. Let me share this. So the equation stated. Let me come down so that you can easily. Oh, what have I done? So
Do you know your voice was breaking?
okay, but can you hear me clear now?
Okay, Henry, we know.
Can you hear me clear now?
We can hear now.
So the equation was
Yes.
y equal to BO. And what's your BO? BO is the coefficient of the intercept. So you say equal to, we want to get y, so y, which is the output, is equal to BO. BO is the coefficient. So you type the value minus 530.722 whatever. Then plus. After plus, the next thing is B1S1. So B1S1 means B1 times S1, which is the coefficient of the second variable times that second variable. So I open brackets to put the times. The coefficient of molar weight 3.091 times the value of the molar weight 270. That is my C5. So B1S1, which is B1 times S1. The coefficient of S1 times the S1. And my S1 here is molar weight. So the coefficient of molar weight times the value of molar weight. Then you put plus, open bracket, the coefficient of hydrogen bond acceptor minus 555 point something times the value of the hydrogen bond acceptor, which is 5. You close bracket plus, you open bracket. Sorry. The coefficient of hydrogen bond donor 129.14 times E23, which is the value of the hydrogen bond donor. So you keep doing it till S log P3. Then at the end, you put your plus and type in your E plus E plus E. The E now is the standard error. So the E is the standard error, which is 349.26 and so on. So this is the model that has been built from regression. So we are using it to now predict our own activity. So once you do that, you press enter. Automatically it will predict the outcome based on the constants generated from the training data. So that is it.
Look at what I want to get clear.
Yeah.
From the formula, you have that you have BO,
Yeah.
BISI plus 2S2 and so on till the number of data you have,
Yeah.
then plus. Now, you made mention of Y. Y is output, Abi.
Yes.
Yes.
Then there is something there's one variable here you call the input. I did not remember.
Yeah, the input are the S.
Okay, S are the input.
Yes, S are the input. S1, S2, S3 to your depending on how many inputs.
Okay. Then these B1, B2, B3, depending, they are the variables.
Yes, they are the coefficients of those your input variables.
No, BO, you mentioned BO to be the
As
CO is the
coefficient.
intercept.
yes, all the B's are coefficients, but BO is the coefficient of the intercept. The intercept. All the B's
Okay,
are this
okay,
coefficient. This coefficient here from Microsoft are the B's. So the BO is that of the intercept. The B1 is that of the first variable, molar weight. The B2 is for that of the second variables, hydrogen bond acceptor. The B3 is that of hydrogen bond donor, and so on.
okay,
So you multiply the
okay,
coefficient by the value of that input, the input value.
okay, okay. Once you add it in that manner, uh, okay,
Is where.
all right. I've heard you.
Okay. So, yeah. More questions?
I beg,
Yeah. Yes, sir.
yeah, Oga Henry, I beg, after this class, make sure you share
Yeah, I will do that because I'm free now. So I will just
you
send the
share
video.
the video
Yeah.
in our email because today I can look through that video.
There's no problem. At least I've settled all my problems, so I'm free. So I will just do that. Yeah.
Okay.
Mm. Okay. Uh, we have uh, we have 33 minutes left. So in the next 30 minutes, in the absence of Kristen, we shall now introduce QSPR. So now, QSPR is quantitative structural property relationship. Quantitative structural property relationship. So, the essence of this one is that we want to build materials that will have unique properties. We want to build materials that will have unique properties. Now, and these properties of a material is also as a result of the chemical descriptors or chemical identities. But then the type of chemical, the idea is that the type of chemical identities we use here will be those ones that directly has impacts on the property we are studying. Like in the just concluded one, we looked at activity, and that activity we are directly impacted by molar weight, TPSA, and others. Now, but in QSPR, we are looking at quantitative structure property relationship. So what kind of property do we want, and what are those variables that influence that property? So that is now what we look at for. Now, you may say, okay, I want to build a material that we, maybe I want to build an absorbent. I want to build an absorbent. So, meaning I want to build a material for the removal of heavy metal. So I want to build a material for the removal of heavy metal. That means I'm going to look for the removal efficiency of my training data, which means I'll look for already used, already known similar structures that have been used, that have been studied against, they have been studied for heavy metal absorption. So once, and the idea is that there must be similar structure. Don't go and start using structures that are not similar, because we want to see the relationship between the structure and the property. So here, when you are using structure A, structure B, different kinds of structure, you are just developing a round model. So if I want to work on materials, compounds that can absorb heavy metal, or compounds that can absorb pollutants like methylene blue. A lot of us have done work on the removal of methylene blue using activated carbon from different kinds of plants. I think such kind of work is rampant everywhere. If not methylene blue, Congo red. If not Congo red, heavy metal. So that one is not is everyday project work in our institutions. So, but you will hardly find pure substance that have been used in this study, because most of the studies we use are always plant materials. But we can go online and search for, okay, let's say we can say still pyridine compounds that has been used for methylene blue absorption. You get their absorption efficiency, mostly their removal efficiency of these different pyridine compounds that have been studied for absorption, for methylene blue absorption. So you get their removal efficiency. Then you look at what properties of that structure influences the removal efficiency. You may identify different kinds of chemical identities. At this time, we may not even be using molar weight or TPSA, because TPSA is for activity. All those ones are really drug-like activity descriptors. So what other factors can constitute in removal efficiency from that structure? We can see if hydrogen bond donor can still play a role, hydrogen bond acceptor can still play a role. So when you get them up to 5 also, or 10 depending, you build a model with your new compound you want to use as absorbent. So here you don't need to waste your money now on that new compound trying to investigate the effect of contact time, effect of absorbent dose, effect of temperature, pressure, effect of pH. You don't need to be doing those ones again. You can just use the model and now predict the absorption or the removal efficiency of your new compound. Now, but there is a challenge here now. When it comes to material science, most of the work done on material science, you barely get work, you can barely see work on similar structures in material science with a given property. You barely see such kind of information. But let's just see how we can develop one. What will help you then is AI tools. Yeah, AI tools can now help you at this stage, because there is no database. There is no database. Unlike, just like the one we did, we typed entrepreneur malaria, meaning that we are targeting entrepreneur derivatives on malaria targets, on malaria activity. There is no how you can type entrepreneur on removal efficiency so that you can get removal efficiency of entrepreneur in PubK. Okay, let us try, but I don't think so. So that is the challenge we have in the QSPR unless we begin to develop such database. All these are loopholes. All these are loopholes for early career scientists to invest, to look after, to look at. So there are diverse areas to study. There are diverse areas to explore. So let me see. Uh, okay, can someone suggest any uh, kind of property we can look at for? Like I just explained on absorption. Do you have anything in mind?
I mean, let's go with the adoption.
Okay. So let's see if we can have entrepreneur. But this is what we are doing is not working. But let's see entrepreneur removal efficiency. Heavy metal. Oh, this will not work. Uh, Only AI tools can help us. Entrepreneur heavy metal removal efficiency or methylene blue absorption. Okay. Let me say entrepreneur methylene blue absorption. We may luckily see something, but so that we will not always be talking about drug. We have diversified chemists here. Okay. Ah. Okay. Hey. Ah. Pop is superhero.
It's not with entrepreneur now.
Let me see.
No carry.
You know, he don't carry anything entrepreneur. He just
No, you just
identified
do
methylene blue.
adoption.
Uh, okay. Marine adder. You see, that is the challenge we have now, eh? And let me just say that in case our next project student, we can change that mindset. Why is it that all the absorption studies we are doing, we don't use pure compound in the study?
Pure compound like
You know, if you are doing absorption, people compare with activated charcoal.
yeah.
Now, why do we always use plant materials to produce this activated carbon? Why can't we use synthesized compound in the remover in that study? That is why we don't have, we barely have pure compounds that have been studied against, that have been studied on remover, on mediation studies. I don't know if you understand what I'm saying.
Okay.
So all our social studies, can't we synthesize maybe two benzophenol and say, okay, I want to study the absorption or the absorption potential of two benzophenol and compare it with activated charcoal. Have you seen such a work? Rather, what we see is activated carbon from groundnut shell in acidic medium or alkaline medium. Activated carbon from groundnut shell, and is not precise
I think
because we cannot still
I think the idea I
yeah.
think the idea is because we are trying to clean up the maybe the contaminants in whatever we're trying to. I think the main idea is because we are looking for a way to remove a pollutant.
Yes.
So use a synthetic compound which might likely bring another contaminant is a problem.
Okay. Yeah. I see reason from there. I see reason from there, and that is why we are screening now. We are doing testing. Not all compounds, not all synthetic compounds are contaminants to an environment. Now, compound A might be contagious, might be a pollutant in environment A, but in another environment it might not be a pollutant. So, since we are removing these pollutants, we can look for synthetic compounds that, if we subject them to this environment, may not serve as pollutants in that they may not be seen as pollutants in that environment, and then still have the ability to remove these pollutants. Now, we can also develop toxic free compounds. We can model toxic free compounds and use them in the absorption studies. We can model toxic free compound. The only reason why people keep going for this plant based is they will tell you they want to reduce waste, because groundnut shell is a waste, so we are using it to to turn our waste to raw material. But then we need data. If groundnut shell activated carbon succeeded, if it succeeded in removing methylene blue, what about the mass production? Maybe now we want to now do a mass production. You know that the groundnut shell I use in Owerri is not the same composition with the groundnut shell in Oka, because of genetic variation and source.
Soy. Yeah.
In fact, most persons don't know this, but let me now tell you that bitter leaf, the phytochemicals of bitter leaf, the one you cultivate maybe from Enugu, and the ones in Owerri will not have the same bioactive compounds, but they will have similar bioactive compounds.
Mm-hmm.
If I do ethanol extract of bitter leaf cultivated in Enugu, and I do that same ethanol extract of the bitter leaves cultivated in Owerri, the same ethanol extract, the same bitter leaf, I will not expect to see the same bioactive compounds. I might just see similar bioactive compounds because of biodiversity,
Environmental
environmental
factors.
factor, genetic variations,
Yeah.
because the phytochemicals of these compounds, they are produced. One of the factors is the soil where they are being planted. The soil where they are planted affect their makeup. I think a work was done on this and was presented at Insota. Yes, a work was done on this. In that study, they collected different samples from different locations and compared them. They saw variations. So if we are claiming to reduce waste with groundnut shell, the efficiency of that groundnut shell we are using from this source will not be the same when we take another groundnut shell from another place. So rather, what we should look out for is what is the component of this groundnut shell that is responsible for this absorption. Because for it to absorb, there must be some functional groups. There must be some functional groups found in, there must be some components, some compounds in that groundnut shell that took part in the absorption. So our research should now shift towards this direction, so that we can have data, we can store those data and say, okay, that compound A in groundnut shell has this so efficiency. So we can have data, but if we keep using crude plant material, we don't have data. We don't have data, and science research is controlled by data. And the problem we have in Nigeria is that we don't store our data. Poor data documentation is part of our challenge here. I've said that before. In our HOD's office, or you go to your school library, you will see a lot of projects done in chemistry department since 1990, when the department started, till today, but there is no documentation of the research findings. They just end there. So now this is the challenge whereby we have in 3SPR. I'm just telling you the challenge we have in 3SPR. So, but there is nothing AI cannot do. So we can just tell AI that we need anthraquinone compounds that has been tested against methylene blue absorption to give us their absorption efficiency. Maybe some persons must have worked on them which we don't know. Once AI gives us those results, we can now validate it, check how true it is. By using other AI tools, you can use ChatGPT, Gemini, QuickBooks, DeepSeek, and
So which
others.
AI would we use? Is it Gemini or ChatGPT?
Which one do you have access to?
To-
Okay, I have access to
I have
this.
Gemini.
Okay. So you can search for all, then compare the result they gives you. If the results here appear there, it means it might be true. Because I don't trust AI result too. Yeah, I don't.
That's it now. You cannot say, if even it would even tell you to confirm, because it even
Yes,
makes mistake.
yes.
So
So
if you are relying solely on AI, the possibility of having like a good data will be very low. Same. Okay.
okay, I'm seeing something here. Electroactive anthraquinone used as electro-modified material for absorption. Okay, not that much. Okay, we'll be left to use AI because maybe entrepreneur have not been worked on. Let's see indole. You just keep testing different class of compounds. See the ones that can give you a result. Okay. Let's just try AI. Let's see. There's nothing you ask AI that doesn't give you answer. Let me say provide in a tabular form. let me start with 10. 10 entrepreneur derivatives and their removal efficiency on methylene blue. You must have an answer on methylene blue. So let's see. You must have an answer, definitely. So I would suggest, okay, I'm sorry, but I couldn't find reliable published data. OCB. So AI is telling me that ChatGPT is saying it can't find reliable informations. So you see, this is a big problem in research. I found studies showing improved efficiency of entrepreneur dyes. Okay, let's work on the entrepreneur dyes. No, entrepreneur dyes is still the pollutant. Entrepreneur dyes is still the pollutant. Like alizarin dye is a pollutant. So if you want, I can track down. Oh, so what kind of property again you think we can investigate on? Maybe on
We have nine
chemistry.
minutes to go.
Okay, I will leave that for you to ponder on. Uh, ponder on it. What kind of work do people do in the lab? Uh, let me see.
Water analysis. So, the pass.
Okay, let's look at coagulants as a property. Water coagulants. Water coagulants as a property. So the factors that uh, getting the structural properties will not be a problem. The first thing is, let's just get similar compounds that has this reported coagulant property. But at the same time too, I've not seen a work where people are doing with pure compounds on coagulation. If we keep working on crude materials, we cannot still explain. I keep telling people around me of the issue of crude material. You cannot explain the interaction between that your crude material that gave rise to your that result. We can't explain the mechanism of the interaction. All what we know is that a purple extract was able to coagulate some solid particles from our wastewater. What was responsible in that coagulation in the purple extracts? That such result cannot tell you. Rather, we spend our money doing SEM, TEM, SRD, EDS. You want to get the structural morphology of the of the sample. We just waste our money, and then you do and you do a lot of work. We should start generating results that can be explainable. That we can say, okay, now this thing for here, now you make them do like this. See where the interaction occur, so that it can be scaled. We can scale it up. We can now do mass production. But maybe in the next 6 minutes, we have 6 minutes left. In our next class, we shall start talking about structure-based draw design. That is the dotting proper structure-based draw design. We shall not look at that dotting, but I will give an assignment. The assignment is
Hope it's not on this one that we don't have data or
no.
eh?
It will be on the activity aspect. QSAR. You yeah you are going to
No give
model.
us 100 basketball.
Okay, wetin be your problem na?
Not say you it not they had it not they had you you just say 100.
But that's how it should be.
And yeah, we have 5 minutes. So.
Yeah. That's how it should be. We
I have a question.
okay, sir.
This last professor you mentioned, QSPR,
Mm.
can it be model to predict uh, the activity and also uh, other property of a novel compound, that has not that the receptor has
Mm.
not been known? Can it be used to predict, like, first of all, use it to predict a receptor where it can function, like if it's a protein or a ligand where it can bind to produce a physiological activity for novel compound?
Yes, you can do that. In as much as you now ask yourself what is your output. The output you are looking at is the binding site, the receptor site. So you have to look for similar compounds, and there must be a training set. So you have to look for training sets which is of similar compounds and their binding sites. So the binding sites of those similar compounds will be your output. Then you want to use it and predict the binding site of my own novel compound. So you can try it. I have not really tried that, but it depends on what will be your output. Now your output is binding site. Yes, your output is binding site. Your output now is no more activity, but now binding site. So you look for large training sets and their binding sites. Now, now these are binding sites should not be on a definite protein. It will not be on a definite protein because you will not look for compounds that have different binding sites on different proteins. That result will be so rigorous. So if you are targeting cancer, maybe breast cancer, and the protein is 5p11, so you get different similar compounds that has different binding site on 5p11. That their grid bus dimension, which is the binding site, will be your output. Then your new compounds, which you don't know the binding site, you want to predict the binding site. This model can now help you and predict the binding site of the new compound. But they must be of the same protein. Both your training data will target your, the data must be from that one protein you are using. So that protein you are investigating will be the protein you will use in your training data. So you look for 100 compounds that has been used to target that protein and get their binding sites as your outputs. So it is possible. I know it is possible.
Okay.
Yeah.
Okay.
1 minute more. One
Yeah.
minute.
Yeah.
Oh,
At this point, I want to appreciate you for coming around. So